Good morning students, I am Dr. Raju Anita, Department of Computer Science and Engineering. Today we are going to discuss about Chomsky hierarchy in automata theory and formal languages. So before we are going to discuss the topic, let us see aim of the session and instructional objectives and learning outcomes. What you are going to learn after completion of this topic and what is the aim of the session and what are the objectives of the session. As we know, the aim of the session is to provide an understanding of the Chomsky hierarchy, its classification of formal languages and its significance in the field of theoretical computer science and in linguistics. Now the objectives: to understand the Chomsky hierarchy and its level of formal languages, to explain the characteristics of grammatical rules associated with each level of Chomsky hierarchy, to discuss the importance of applications of the Chomsky hierarchy in language theory, parsing and the study of formal language recognition. Learning outcomes. What are the learning outcomes? After completion of this session, what you could able to learn? To identify and describe the 4 levels of Chomsky hierarchy: type 0, type 1, type 2 and type 3. Difference between the grammatical rules and restrictions associated with each level of Chomsky hierarchy. Recognize and characterize the examples of formal languages within the Chomsky hierarchy. Analyzing and evaluate the practical implementation of the Chomsky hierarchy in parsing, language recognition, algorithms and the study of the natural and programming languages. Let us see the Chomsky hierarchy. What is Chomsky hierarchy and how we are going, the languages are accepted by the values, that is grammars. So let us see here the diagram of Chomsky hierarchy. Then we can discuss about the linear bound automation. So here this is the Chomsky hierarchy. We can see here this is the regular language, context free language, context sensitive language, and here desirable, Turing acceptable and non Turing acceptable. So if we are taking this is grammar's type, then we can say here this is type 3 grammar, and this is context free grammar is type 2 grammar, and this context sensitive grammar is type 1 grammar, and this are type 0 grammar. So what we are going to see here is type 3 grammar. These type 3 grammars are accepted by finite automata. So whatever the regular languages, those regular languages are going to accept by the finite automata. And here you can see context free language. These context free languages are type 2 grammars. These type 2 grammars are accepted by, here we can see push down automata. Push down automata. This push down automata is used to accept the type 2 grammars. And next type 1 grammars. This type 1 grammars are context sensitive free grammar. This type 1 grammars we are going to discuss. That is linear bound automation. Linear bound automata, it will comes under type 1 grammar. And type 0 grammars are unrestricted grammar. There is no restrictions. Those are Turing machines. Turing machines will come for unrestricted grammars. So here we can see, as per this we can see here we are discussing the linear bound automata. The linear bound automata is comes under context sensitive grammars. So these context sensitive grammars is, we can call it as type 1 grammar, right? Here we can see this is the type 0, type 1, sorry, this is the type 2 grammar. So this type 2 grammar, so we can call it as this is the type 2, but we should not do like this because some of the students are getting confused of this. So we are calling this one as type 3 grammar, and this is type 2, and this is type 1 grammar. These are the type 0 grammars. So we can say that context sensitive grammars always comes under type 1 grammar. So these type 1 grammars we are discussing in LBA, linear bound automata. So I think this is very clear that type 0, type 1 and type 2 and type 3 grammar. So let us see what is this context sensitive grammar. These context sensitive grammar, there is some restriction is there. So in this context sensitive grammar, the grammar will be alpha less than or equal to beta. That is the length of alpha is always less than or equal to the length of beta. So here you can see alpha, the length is less than or equal to length of beta, means the right hand side of the grammar and the left hand side of the grammar. This is called the left hand side of the grammar and this is called the right hand side of the grammar. The left hand side of the grammar, the length always should be less than or equal to the length of the right side of the grammar. Suppose if you are taking AA implies BAB. So you can see here AA, what is the length of here? This is the 2, and what is the length of this? This is 3. So we can call it this is the acceptable context sensitive free grammar. But here this is restricted for A implies epsilon. So unless it is the start symbol, we are restricting such kind of productions in context sensitive grammar. So what kind of language we are using to accept such kind of context sensitive free language is linear bound automation, LBA, linear bound automata. So you can say that what is this linear bound automata, how it is differ from Turing machine. As we know, the Turing machine is type 0 grammar, right? Type 0 grammar is our Turing machine. This LBA, linear bound automata, is also just like a Turing machine. What makes it as the difference between the Turing machine and linear bound automata? The first difference, let us see what is the difference between the Turing machine and linear bound automata. So the first difference is there is an input tape. So there is an input tape for linear bound automata. So here you can see linear bound automata same as Turing machine with one difference, the input string tape space. So Turing machine is also having input string tape, but the difference between linear bound automata and Turing machine is there is an input string tape space. This is only tape space allowed to use. So there is a restriction. This is a non-deterministic logic it is going to follow, and there are some end markers, left end marker and right end marker. For example, if you are taking the input tape, here this is an input tape. Assume this is an input. Wait a minute, let me take okay, this is the input tape. So if you are taking the input tape here, so here I am taking the input string A, B, C, C like this. There are some boundaries are there. For example, the boundary I am giving $$ symbol. So this is the left end marker. This is called it as left end marker. End marker, and this is called it as a right end marker. Right end marker. So there is some restrictions for the input space. This is the input space. There is some restriction it is given. So here the finite control is moving from here. So whenever the finite control is moving towards to this, it doesn't allow to move outside of this right end marker. So this is the end marker for it. The finite control cannot move. So it will not cross the limits. So these are the limits. Linear boundary I am giving here for the input space. Because of this reason, we are calling this is the linear bound automata. There is a restriction that was given for that input space. So that is the main thing, the difference we can notice here. And the second one is it determines only non-deterministic logics. That's why we are calling this is the linear bound automata. The linear function here is boundaries. And here let us see some examples of this, and then we can see how it linear bound automata will works. So before going to that, LBAs as non-deterministic. Non-deterministic LBAs have a same power as deterministic LBAs. So this is the open problem they are giving. Let us see one by taking one example problem. So here I am taking one example. The example here is L is equal to let us take one example. L is equal to A power n, B power n, C power n, such that n greater than or equal to 1. This is my example which I was given. So this I want to apply the linear bound automata to design the to find a language which it is acceptable with the string. So first of all, we need to write the language for this. So what kind of languages it will accept? For example, n I am taking 2. So AA, and then here I am taking wait a minute, here there is some restrictions it came. Let me take here. Okay, now AA and then BB CC. If I am taking here 2, n value 2, my string is AA BB CC. So this is the first string what I have. So what is the second string you have here? Suppose here I am taking n value is equal to 3. What it will be? L is equal to A 3 times A, 3 times B and 3 times C and so on. So right, these are the different strings that is there in L. So now let us take one string and then see how this is acceptable by the linear bound automata. Okay, so for that I am taking here the string here is L is equal to AA BB CC and then I am applying here linear bound automation. So here I am taking L is equal to AA BB CC. So what I am taking here, n is equal to 2. Whenever you are taking n value 2, that string is AA BB CC. Now I am using here the input tape. You have to see that input tape. So what is the input tape I am taking? AA BB and then CC. This is the input string which I am taken, and fix the boundary. You can take any symbol as a boundary. For example, I am taking the boundaries are less than symbol and greater than symbol. So now the finite control tape. This is the finite control tape. It is moving towards to right hand side and left hand side. So just like a Turing machine, the finite control also moves towards to the right hand side and as well as the left hand side. Now if it is moving to the right hand side, if I would like to move to the left hand side, we can move towards to right and towards to left. That is the main theme of the Turing machine. The same we are following for the linear bound automata, but only the restriction here is the boundaries. The finite control, it should not move outside of the marker. This is the left hand marker and this is the right hand marker. So the finite control should not move beyond these markers. That is the main thing we need to remember. So for this, let us see how we are constructing the linear bound automata. So first, let me take here, you should design a linear bound automata. So for that I am taking a tape AA BB CC. This is my string. So I need to check whether it is acceptable by the language or not with the help of linear bound automata. So initially my finite control is pointing to here, that is the left end marker. So first of all, take it here. This is the Q naught. This is the state which I have, Q naught. Now I am in the Q naught state. In this Q naught state, after reading the this end marker, left end marker. So whenever you are reading the left end marker, you are keeping the left end marker as it is and moving towards to right. So this indicates the first symbol. Here I am having 3. The first symbol indicates left hand marker and we are keeping the left hand marker as it is, and then we are moving towards to the right. First of all, to understand this one, we need to understand the linear bound automata is how many tuples. As you know, finite automata is general is 5 tuples, but the linear bound automata is having Q, sigma, tau. This is called tau, and then Q naught, and then Q accept and Q reject. This is called this Q accept and Q reject. So we can also call it here, this is 2, we can say, we can also mention as left end marker and right end marker, left end markers and right end markers. So this is the tuples you should know before. So let me explain very clearly with this, so no clumsy here. And here I am writing here M is equal to Q, sigma, and then you know delta. Tau is there. Tau is the tape symbol what we are having. Q naught is the initial symbol what we have, and then here Q left hand marker. We can also write here as M L, that is M left hand marker, M right hand marker, M left hand marker and M right hand. This is the transition functions. Tau is the tape symbol, Q naught is the initial state, left hand marker, right hand marker, input. Sigma is called the input symbol, Q is the set of states. So here these are all the different tuples that what we have in the M. So now we need to understand here how this will be work here for linear bound automata. So for that, here I am writing here clearly again. So first my tape and my tape input is here in the left hand marker. So I'm taking here Q0. So Q0 is the, here I am taking Q0. So now Q0 initial state, I am here in Q0. So in this initial state, after reading the initial state, after you are in the right initial state, after reading the left hand marker, what changes you are doing? First of all, we have to understand the logic. So the logic behind here is, so whenever my finite control is moving to here, I found A, then you have to mark it as capital A. That means you are making this as a capital A, and then you are moving towards the right side of the tape. Whenever you are moving the right side of the tape, what it will happen here is it will move here. So there should be one B and one C for every matching of A. That's why I'm moving towards the right hand side, and then move towards to here, and then move towards to here, and then move towards to here, and finally move to the end of the tape. Whenever it is moving to the B, it has to mark it as B, capital B, and whenever we are moving to C, it has to mark it as capital C. What it means, for every A there is a matching of capital B and there is a matching of capital C. So for one A there should be match of one B, and for one A there should be one match of C. That means there should be the match of one A, B, C. If you are taking again A, there should be the match of B, there should be the match of C. So for this A, it should be matched to B, which should be matched to C. For this A, it should be matched to B and it should be matched to C. This is the logic behind our problem. So based upon this logic, we need to implement. So how we are going to implement here is, again I am taking here. Now let me take again the tape. Now here this is my tape space. A, B, B, and then C, C, and left hand marker, right hand marker. Now my finite control is here. Now initially you are in Q0, and then you are reading left hand marker, and then you are keeping left hand marker as it is and move right. So now my tape control is pointing to A. Now I found first A. I need to convert this into capital A. So for that we are moving to next state Q1, and here in this Q1 what we are doing here is that A is converting into capital A and moving towards to right. Now you are in Q2. Right, so Q1 is over. Now I found small a, but small a should not change. Whenever you are not changing, keep that A as it is and move towards to right. I am moving towards to right. Now after that I found B. So whenever you found B, keep B as capital B. So small b is converted into capital B and then move right. And now here you are in Q3. Right, now I move towards to this. My finite control is moving to the next B. So there is no change in the next B. So keep B as it is and move towards to right. Now I found C. Whenever you found C, you need to convert C into capital C and move left. So my tape marker has to move left now. And right, here you are in now Q4. Right, now I found whenever I turn left, the first symbol I found is B. So B, you should not do anything. So I am keeping as it is here B, and then B, move left. I am moving towards to left, and I was moved toward to left. Now I found capital B. So you should not do anything. Capital B, keep capital B as it is and move left. I move to left. So I found small a. Do not do anything. Small a will be small a and move left. Now I saw capital A. Whenever you saw capital A, again you have to move towards to right. So here I am moving here. Whenever you are seeing capital A, and keep capital A and move towards to right. So now I am here. Now your tape will be looks like this. See here, A is capital A became capital A, and small a, B capital B, small b, and capital C, small c, and left hand marker and right hand marker. Okay, now you are here. Right, now you have to move towards to right. Again I found small a. The same it will be repeat. So whenever you are seeing small a, again it will move to here, and now A will be convert, and now you saw the capital B. so I need to be as it is, so I am writing capital B will be as it is and move right. Now I saw small b, whenever you saw small b, it is converted into capital B and move right. Now capital C, whenever you are seeing capital C, that capital C has to be same as it is and move right. So I am writing here capital C and then capital C has to and move right. Now I am seeing again C, so small c is converted into capital C and my tape control move left, right. My tape control move left. Now I am seeing small c, whenever you are seeing small c and keeps I am seeing capital C, whenever you are seeing capital C same and move left. I am moving towards the left. Now I saw here I saw capital B, whenever you saw capital B, move left. So like this you are moving up to here. So after this my tape control will be like this. So after here my tape control, how it will be, the tape control I would like to show here for you. I'm changing this and then here I have B, capital B and move right. Okay, now my tape control will be like this. A and then it is became A and then it is became B and C, capital C, left hand marker, right hand marker. Okay, my B is converted and it is moving here. Now my tape control is here. Whenever I found capital A, keep capital A and say, now I did not found anything here. I did not found anything. I found B. So what I have to do here, whenever you found capital B, keep capital B as it is and move towards to right. And now this it will be Q5. Now after B again I found B, so again if you found B, keep B as it is and move right. And now I found C, capital C and move right. And then you find left hand marker, keep left hand marker and move right, and then you are saying that halt. So I am halted this program. So here I halted this one. So you understand this one. And then here this is the diagram which it is given for LBA, linear bound automata, to accept the language AA, BB and CC. So I am explaining again this one with the help of the diagram. You can concentrate on this. Here I am taking eraser and let me erase this. This diagram you can clearly understand if you are understanding the movement of the tape control. See here, first I have my tape here A, B, B, C, C. Right, there is a markers left and right. My finite control is here first. So whenever you see the first finite control, then you are keeping the left hand marker as it is and moving right. So it is moving towards to right. Now you are in Q1. So first A, whenever I am seeing the first A, it is converted into capital A and moving right. Now in small a. Now whenever you are seeing the small a, you are keeping small a as it is and moving right. And now you find small b. Whenever you saw the small b, convert into capital B and then move right. This is tape control is moving towards to right. So now small b, whenever you are seeing the small b, it will be keep as it is and then move right. Thus it will be done. Now small c, whenever you are seeing the small c is converted into capital C and move left. Now my tape control is moved towards to left. Now I saw small b, keep small b as it is and move left. Now I saw capital B, keep capital B as it is and move left. Now I saw small a, keep small a as it is and move left. And if you saw here already capital C and then we are moving left. So finally I saw capital A, then move capital A, keep as it is capital A and move right. So after this first iteration, my diagram it will be like this: A and then small a and then here capital B, small b, capital C and small c, and left hand marker and right hand marker. This is my diagram when I am here. Now here I found capital A and moving right. Now I found small a. Again this iteration it will be repeated as it is until your tape control is having all symbols are marked as capital and small. So finally after this iterations, then I will get here the tape control will be like this: capital A, capital A, capital B, capital B, and capital C, and capital C, left hand marker, right hand marker. So now here you are seeing this. After completion of this, now you are here in Q1. Now all are converted. Now whenever you are seeing B here, then B as it is and move right. Again B. So you have to keep as it is and move right. C, you have to keep C as it is and move right. And then whenever you are seeing this left hand marker, we should not move beyond this. That's why we have to keep this L, left. You are not allowed, the tape control is not allowed to move right whenever it identify the end marker. So keep L and halt. This is the problem how we are going to design the linear bound automation. Now let us see here. So what are the different applications that we can do for this linear bound automata? See here, MCQs, there are some MCQs you have, and you can go through that MCQs and which level of the Chomsky hierarchy describe the language. And here there are some different kinds of MCQs are given. Terminal questions: discuss the purpose of the Chomsky hierarchy in language theory, and how does the expressive power of language change as we move up the Chomsky hierarchy, and discuss the implementation of the halting problem in computational theory. And halting problem we solve for all Turing machines, and why not. Halting problem we can discuss there, because some Turing machines, whatever you are giving linear bound automata, halting will not be done. There the problem, it will become the halting problem, that there is no halt, it will be always, it will be there in the iterations only. That's why the halting problem it will come. So thank you for the session, and the session is completed.